In this video, we're going to discuss the second assignment and how we got to the solutions on it. This had to do with creating a logistic regression model to predict a class of an instance of an iris flower presented to it. There were a handful of tasks that were associated with this assignment. This assignment should have been completed by creating a new Jupyter notebook from inside of Anaconda, loading the iris data set using the scikit-learn sample data sets with a link as to how to do that. Plot the data set just to visualize it so that you had some intuition as to what the data set was going to look like, along with a link to do some visualization of that data set. Creating a testing and training data set using the train test split method in scikit-learn, and then explaining your methodologies throughout the training of the model and selecting the samples, basically the percentages that you used, and if you used stratify and what that did to your data set. Then you use scikit-learn to train a one versus rest logistic regression classifier model on the iris data. And once again, there's a link to some examples in scikit-learn how to do that. And then use matplotlib to plot the results in a scatter plot. This was probably the one largest thing that people had an issue with into what to do, and I'll discuss that as to why I chose the method I chose. There's no one right way to do this. What you're trying to do is get the most information out of the actual execution of the model, so you can determine how it performed visually. I asked you to format your code to PEP 8 guidelines. This was not something that you were graded on. PEP 8 is a standard in Python programming that people try to follow as much as possible. I didn't necessarily follow PEP 8 in my descriptions of my code that I wrote, but it's a good set of guidelines to follow. Ask you to comment your code and to add in heading and markdown cells throughout your notebook to basically treat it as a report or presentation more than just a program. So to start off with, after you create your Python notebook, I started copying and pasting code from the various links that I provided, and there were some components in there that weren't needed. Generally, it's a good practice to go through and remove any imports that you don't use in your code. For example, I deleted out all the various models that weren't used in this notebook. So all that was left in this section, for example, is the import of the logistic regression classifier. So importing sys, just as we did before in the assert, to make sure we're using at least Python 3.5, which is all that's required for the components in this module. So if I go ahead and run this cell, that gets my imports done, and it also sets up the matplotlib magics to allow for inline presentation. It also sets up the labels for my matplotlib plots that I use throughout the program. So the first component of this was to import the iris dataset from the scikit-learn datasets functionality. So using load iris is all we have to do to accomplish this. Once again, I copied this out of the link that was provided. So there's my iris equals datasets.loadIris, load only the first two features, and then set the y variable equal to the set of targets associated with the iris data. So we made some changes here to this code, or made some additions to this code. So we loaded all of the data in X, all of the features in X, and all of the labels in Y. And then we used train test split to split up the data set into X train and X test, so the features to train on and the features to test on, and then the labels to train on and the labels to test on. So we take in the features matrix, the Y vector of labels. We specify that the testing size in this case is basically a third of the data. So we train on 2/3 of the data, we test on 1/3 of the data. We use random state to ensure that the split is the same every time we run it, to remove variability from the model as we're training and testing it. We specify shuffle to true so that we don't take in the data in the same order that it's presented from the data set. We shuffle them around randomly using random state so that we end up with a variable presentation of data, so we don't train on the data in the order that it's provided. And we specified stratify equals Y. So stratify in this particular case gives us the ability to create sample sets so that the percentage of each of the classes provided to the model for training and testing is roughly the same between the train and the test splits. That way we don't end up overtraining a model on some classes and undertraining it on others, and then have the testing data suffer from the same variation on it. So one of the things that happens when we specify stratify is stratify isn't a true-false property telling you to stratify. Stratify provides the set of labels that you want to stratify across. So in this case, we pass in the vector of labels, and the function train test split divides them out so that the testing set contains 2/3 of each label, or excuse me, the testing set contains 1/3 of each label, and the training set contains 2/3 of each label as a quantity of each label provided in that label vector. So this ensures that we get a somewhat consistent set of data as much as possible between each of the classes to train on. So when we run this, we end up with our X-train, X-test, Y-train, Y-test already built. Then we take the plot code. So I'd provided a link for some plotting of the data to produce a visualization of it, and I made a few changes in here on this code. So we plot the features versus each other. So in this case, we plot the sepal length versus the sepal width. So we plot sepal length on the x-axis, sepal width on the y-axis. And then we color each of the points based on the class label associated with it. So then we set our labels for our plots that get presented. We tell the matplotlib library for this particular plot what its x min and max values are, its y min and max values are, based upon these calculations up here. And then we go ahead and create the plot. So we create the plot in this case using principal component analysis. So we plot our figure, and then we create this 3D visualization of each of the three most influential combinations of values, just so we can kind of get a feel for what the 2D versus 3D breakdown is. This wasn't necessary, but since we've already covered PCA to a certain extent, I wanted to go ahead and throw this in here. And once again, this was copied directly from the IRIS dataset code that was in the link in the exercise. So if I go ahead and run this, I get my 2D plot, and based on what we saw before in class, the first class that, is completely linearly separable, all these red dots here, from the other two classes, which are interspersed throughout with no really good explanation as to how you would tear these things apart into class 1 versus class 2. But if we take a look at the PCA breakdown, we can see where using these three different eigenvectors over these three different principal vectors between these three different labels, it starts to look like we could create some hyperplanes between these data sets that would allow us to more readily separate our three classes better than just using the two labels in and of themselves. So we can, through PCA, generate features that we can build the model off of, as opposed to just using the two features provided in the data set. So at this point in time, it's time to create the logistic regression classifier, and there's the default code that we copied from, or we based this on from scikit-learn, starts off with a C of 10. And once again, I largely copied this code. What I did was I removed everything except the one versus rest classifiers. So I deleted everything that's highlighted there, and I deleted everything that's highlighted there, outdented it, and then made some changes to the code to remove all the stuff that it didn't need, now that we're not plotting all four models in the sample. And then basically train the model, which I named LR_OVR logistic regression _one versus rest. So we create our plot, we fit the model, and then we go through and predict what the label will be using the test data set. So we fit it on the train data set, and then we predict it using the test data set. And then we calculate our accuracy score, which in this case um, is mean square error. And then we, for each class, we produce a scatter of the probabilities for each of the probability distribution for each label. This part wasn't necessary, but because it was already in the sample model that we built, I went ahead and included it in there. So we can run that, and that produces our probability density distribution for each of the classes in the model. And then I produce the scatter plot. And in this case, the scatter plot is simply on the x-axis, we're presenting each one of the samples across the axis. And then on the y-axis, we are presenting the predicted label. And then we're coloring it with the actual label so we can visually tell which model or which labels aren't in the right class by color. I had a little bit of a challenge looking at the test points, so I changed the size to 150 pixels to make it a little bit more obvious when it was executed what the result was. So when I run this, I get nice big dots, and I see for class 0, every instance of class 0 in the test set is properly classified red, so it's good there in terms of that. Then when I start to look at class 1 and class 2, I see some outliers. So class 2 is orange for the proper classifications, but there's the odd grayish dot in there indicating false positives for that class. And then if I look at class 2, which is the gray class, I see a couple of orange values in there indicating false positives there. So using just sepal length and sepal width, we see that we have some improper class labeling going on. So one of the things that we can attempt to do at this point is go back up to our loading of the data set, and instead of using just the first 2 features in here, what if we use all 4 features? So if we look at X now, instead of having just the 2 values, now we've got all 4: sepal length, width, petal length, and petal width. Now we've got all 4 values to operate off of. So I don't want to try to visualize and plot this like I did before, because I can only plot 2 dimensions, at best 3 dimensions in real life. I can't plot all 4 of those. So now that our data set has all 4 features in it, we will go through and recreate and retrain the logistic regression classifier using all 4 features and see what happens to our performance. So we'll retrain it and then reproduce our scatter plot. And what we notice this time is that instead of having 3 or 4 gray points inside of our class 1 predicted class. We only have one, and we have 2 misclassified labels in class 2. So we've got a much better accuracy of prediction for our model in this case by including all 4 features instead of just the 2. And you can fiddle around with this and determine whether or not all 4 features outperform using just the eigenvectors for 2 classes instead. So there's a lot of steps that you need to take when building a model to test all the different variants of how to present features to the model to predict how it performs. But this general format presented in this video is what the basic requirements of the assignment were meant to achieve. And I will put this Jupyter notebook on the Canvas site for the assignment as well, so you'll have it for future reference. Thanks.